Hello, everyone. Thank you so much for coming to this graveyard shift. You have to tolerate me for the next two presentations, and the reason is the students who were supposed to present this unfortunately couldn't be here, so I took it upon myself to do it on their behalf. The first one is looking at the statistical distribution of residual stress and microstructure in welds. So the reason we wanted to look at this, I don't think we didn't put a context slide on this. So the reason we wanted to do this was because there was this relatively large Horizon 2020 project. And the whole point of it was to go towards a probabilistic assessment of the welds. And the reason for that is our power plants are aging, they are falling apart, there is a shortage of gas, if I may say so, and we have to keep these rickety old power plants going while making sure that they don't fall apart. So if we go and look at the lower bound fracture of welds, we end up closing power plants that are safe to run, and therefore it's more desirable that we work towards a probabilistic approach and then do a risk-benefit analysis. You know, can you live with a weld maybe breaking 0.1%? If you can, probably you can extend the life of that thing. But looking at this probabilistic assessment, it means that you have to look at the variation in everything, variation in residual stress, variation in fracture toughness. You have to do a lot of sensitivity analysis for all of these. And we spent 4 years as one of the work packages trying to figure out what is the variability in weld residual stress, because we wanted to put it in our probabilistic approaches. And I want to show you how I wasted 4 years of my life. There you go. So this is part of that project. You go to a shipyard because they don't let you to go and do this on a nuclear power plant usually. You go to a shipyard and you get lots of plates, 9 of them, and you get some welders to weld them. Exactly what happens in reality. So you get some welders who are very experienced. You get some welders who are apprentices. You weld some of them in the lab, you weld some of them outside, you weld some of them when the guy is sleepy, you weld some of them when the guy is fresh out of his breakfast, to see what variability you're gonna get. So 9 plates in all different conditions. They were welded at a proper shipyard, and they were submerged arc welding. This is an amazing picture. I'm sure you haven't seen this before. You know, this is how nice a weld in a plate looks like. Right, okay, moving on. Then you spend a lot of money buying lots of beam time at synchrotron facilities, because if you go to them and say, I want to measure this identical 9 scientifically, could you please give me government budget to do this? They throw you out. So you go and buy industrial synchrotron time, you stick all your welds in there. This is EDXT, really, really high energy, 50 to 150 kV pink beam, so it can get through a hunk of a steel. Still, the gauge volume is not that big, it's 1 mil by 1 mil. So we are averaging over 1 mil by 1 mil. And we measure the residual stresses all over the place. I don't think this is very clear here. This is longitudinal, this is transverse. Surprisingly, the guys who are welding things are really good. You know, although despite all the things you have thrown at them, you don't get much variability in the weld residual stresses. Just for good measure, you go and get the contour method and also do all of them. So I don't want to go through the contour method. You end up with around 56 megapascal plus and minus variability in your weld residual stresses. This is how the residual stress, the weld microstructure looks like. This is a complete mess. So it was a very nice, well, not a very nice, but it was relatively nice ferritic material, and you get a torch to it, you melt it, you solidify it, you do it over and over again, you end up with a mess. So this mess has a lot more variability than the original plate. So how do you measure the variability in your material microstructure? Well, you go and get some sharp impact samples. You do loads and loads and loads of them in the parent material, in the weld material, at the bottom of the weld, at the top of the weld, in the middle of the weld, on the top of the sample, bottom of the sample, and you go and do all those Sharpie tests. I am not trying to get the fracture toughness of my material from here, because that is a minefield. I don't want to jump into that minefield. All I want to do, this is a surrogate for my material variability, okay? So I'm using the Sharpie test as a surrogate to assess my material variability. The material variability in the weld is 16.5 plus or minus 3 joules, and the parent is actually not that much lower, 14.8 plus and minus 3.1 joule. And then we go and do some fracture tests. So we did variability of residual stress, we did the variability of the microstructure. Now we go and get variability in the fracture toughness of the material. Ferritic material, nice, relatively brittle. So you get loads of CT samples out of it. The weld is bang in the middle. You don't have to do a ASTM 1820 loading and unloading and all those things, because the crack propagation before it goes unstable is not that long. So this is how much this is the original crack. This is how much it grew before it went bang. So you can go and use ISO 12135 to estimate your J integral from your just pull the CT sample open and break it, rather than a complicated loading and unloading. Right, so what happens is you get your parent material variability of CT samples, you get your weld material fracture toughness variability. So this is the probability of fracture, this is the stress intensity factor. The black line is the parent material, and the dashed line is the toughness. As you might expect, you have residual stresses, you have a little bit of tougher material in the weld, so your fracture toughness comes down. And not surprisingly, the variability in the fracture toughness of the weld is more than the variability in the parent. But the question is, who is responsible for this variability? Is it the residual stress, or is it the microstructure? Did I waste my life 4 years of my life trying to find the variability in the residual stress? Should I have, hello, coordinator, should I have measured the variability in the microstructure? I don't want to go through this, but it's too complicated. You get a really clever PhD student, and he goes and spends a year studying statistics, although he's doing a mechanical engineering weld project. And he comes up with principal component analysis, which can tell us, I have a variability in my material, let's call it fracture toughness. There are two components that cause this variability, the variability in the microstructure and the variability in the residual stress. Which one is more important? And this principal component analysis can tell you that. And you wouldn't be surprised to know that this line here, what it says is your Sharpie impact test has a lot more to do with the variability in the toughness than your residual stress variability. So what I wanted to conclude is, when we are welding, we are changing the microstructure and we are putting the residual stress in. Surprisingly, without these fancy new atomized techniques like electron beam welding and laser welding, the guys with the sticks, they are really good. They very consistently weld things. So the residual stress variability in your weld is not much. However, the variability in the microstructure is a lot more. And the fracture toughness variability that is important for our probabilistic assessment of our nuclear power plant is dependent a lot more on the microstructure than on the variability in the residual stress. So, and I think that's me. Thank you very much for listening.
Thank you very much.